Welcome to lecture here. We'll get started in just a sec, continuing on with kinetics. Okay, so last time we started continuing on talking about kinetics and so we got into, again, how to solve for the actual rate law using experimental information. And remember that when we do a rate law, which again, slightly different than the rate expression, which sort of deals with everybody in the equation or reaction. The rate law, as we saw, really only deals with the reactants. Um, so it's only the reactants that are involved in the actual rate law, and the orders, which again, in the case of the rate law, does not come from the balanced chemical equation or the coefficients. They do need to be found experimentally. And as we saw in a couple of different examples, typically speaking, you will be given some type of data table in kinetics type problems. And using those tables and the information, again, usually will consist of really three pieces of information usually. The concentrations of both reactants, or maybe three reactants if you have three reactants, and also the initial rates of each of those along with the trial numbers. So usually there's like experiment one, trial two, trial three. And again, we talked about sort of mathematically how you can solve those type of problems. And again, just to double go over that there, we want to choose two entries from the table. And again, doesn't necessarily have to be the first and the second one. It could be any two entries in the table. But really the key is to choose two entries where one of the concentrations remain constant and the other one varies, in a case where you have just two reactants. And the point of that is so you only have sort of one unknown to solve for. And you basically could do that rate 2 over rate 1 sort of mathematical approach to it. When you get down to the end, you'll have like, 4 equals 2x or something like that. And again, you could do the natural log of both sides and divide it if you want to get sort of if you don't really have really pretty whole numbers, which most of the time you will. Again, as we talked about, if you sort of take the larger rate on top there and put all the values there in terms of the larger rate, that usually will result in, you get in more like nice whole numbers. Well, not always, but most of the time. And we could use that to figure out the orders of both reactants or three reactants or however many reactants you may have. And once you do that, you then will have the completed rate law, from which you can figure out the overall order of that reaction by adding the orders of each of the reactants together. And once you do that, you will then be able to also find the actual value of the rate constant. And again, at that point, once you've had the completed rate law, you could go back to that table that they gave you. You could choose any entry you'd like in that table, entry 1, entry 2, entry 3. And again, if you put all that information into your completed rate law, you should end up with the rate constant. And again, if you choose entry 1 or entry 3, it should give you the same K value, as it's a rate constant. So truthfully, as long as you don't kind of, play with the temperature or anything like that, if you keep the temperature kind of the same, it should obviously be pretty constant for that reaction. Then we started talking about sort of specific orders of reactions. And the first one that we talked about here is one that we saw when we were talking about nuclear chemistry as well, but it's first order kinetics. And again, in nuclear chemistry, all radioactive decay follows first order kinetics. And some important things about these sort of different orders of reactions. There's important things that help you determine sort of what the order of the reaction is. And then if it is, there's certain equations that go with it. So the first major sort of thing that will sort of point you in the direction of a first order reaction is if you actually have the rate law given to you, obviously you can see that there's, a reactant to the first power. If you're not, but you're given the rate constant, which is that little k, and that little k typically will have units of 1/seconds, or really 1 over some unit of time is the typical units that you associate with a first order reaction. And as I mentioned last time, and maybe a couple times before as well, again, a lot of times they may not just straight out tell you the order of the reaction, but they will give you that rate constant, and you're supposed to just sort of know in terms of the units of what type of order the reaction is. So that again is an important piece of information that may not be sort of explicitly spelled out for you in a problem, but if you do see that K, you want to really pay close attention to the units. It will sort of give you an idea in terms of the order. Again, we sort of talked about last time, 1/seconds is like 1 unit on the bottom there. It's like first order. We also saw that 1/molar second is a typical units for second order, like 2 units on the bottom there, second order. So it's a good way you could kind of almost figure it out as well by the number of actual units that you see. Will oftentimes help you out there. Now, if you do identify as first order, they're sort of sometimes referred to as integrated rate laws, which are basically time and concentration dependency on each other. And that's what we have here in the circle on the right. That is natural log of A equals the natural log of A naught minus KT. The first A there is sort of like the final concentration. The second A there is the initial concentration. K is our rate constant, and T here is time, not temperature. So T is time here. And like we talked about in sort of nuclear chemistry, you do want to watch these two guys in terms of units. So sometimes the rate constant may be in a certain unit of time. The time obviously will be maybe in a different unit of time. So you do want to always make sure that they are the same units, especially when they go in there together. Otherwise, again, things will not cancel out correctly, and you'll be off by some type of factor. There's also a half-life equation, which is at the top, and we'll see it again in just a second, but the half-life equals the natural log of 2 over K. And again, that natural log of 2 is sometimes just kind of spelled out as 0.693, which is what you get when you take the natural log of 2. And so sometimes you'll see it like that. And as we saw in nuclear chemistry, a couple things with these formulas. You oftentimes have to kind of use them together in problems, not 100% of the time. And as we also saw in nuclear chemistry as well, although in this chapter, probably a majority of the units that you'll use for A, for example, will be molarity or concentration. But as we saw sort of in nuclear chemistry, you could use grams, milligrams. You could even use those rates, counts per second, so it doesn't necessarily always has to be sort of concentration, but typically when we kind of focus in on chemical kinetics, we're doing regular chemical type reactions. So usually we think of it in terms of molarity as being the unit that's there. But as we saw sort of in that nuclear chapter, it can be a wide variety of sort of units that you could place into there. Now, when we do rearrange that equation, that natural log of A equals natural log of A naught minus KT, we could rearrange it like we do on the left-hand side there, and we could rearrange it in the form of a straight line. And that gives us our y equals mx plus b, where we get our typical graph that we associate with first order, which again is this graph here on the right. On the y, we graph the natural log of A, and on the x, we graph t, which is time. And that should yield you a straight line. And the slope of that straight line will equal minus k. And since you can look at that line, it is a negative slope. I'm not sure if that translated right on your side, but a negative slope basically means that our slope value will be negative. And since the slope equals negative k, negative and negative will give you a positive value for k if you sort of solve for it off of the graph. Another graph that is also technically a first order sort of plot, although most of the time when we do kinetics, we really do aim for that linear sort of plot. But this plot over here on the left is also one associated with a first order reaction, and that's just the concentration versus time. And what we see there is the concentration versus time. We do see over time, the concentration of our reactant starts to decrease, which is what we would expect it to sort of happen in a reaction, right? As A goes to the products, it should start to decrease with time. So again, the important pieces of information as we talked about from this sort of table here or this chart is really the important information that you probably remembered already from nuclear chemistry. you should know obviously the integrated rate law, the half-life equation, the units associated with K, and obviously the graphs that are associated with first order. Any questions on that stuff we talked about last time? Here again is a typical sort of first order plot here. We have the natural log of the N2O5 on the left, or the Y, and on T we have our time. And again, we get a nice linear relationship there. And if we took the slope of that line, you could do rise over run, right, which is what the delta Y, delta X is, to calculate the slope. And graphically, you can determine the rate constant from the graph if you had the right amount of information. All right, so why don't you try one here? So the reaction 2A goes to B is first order with A, rate constant of 2.8 times 10 to the minus 2. How long will it take for A to go from 0.88 to 0.14? So take a couple minutes to see what you come up with. Okay, so let's take a look here. So obviously it tells us it's first order. Again, a reminder that if it didn't actually tell us that, they do give us the value of K, and just from the units associated with K, that should tell you that it is first order. So again, may not always sort of tell you. That's why, again, it's really important to remember what these units associated with the different orders are. And that will help you choose the right sort of equations. Since we've only talked about first order so far, there's not a bad choice, hopefully, that you made. You probably want to use that first order equation there. And in this particular case, we do have everything but time, so we can solve for it. Remember that this first one is sort of our final concentration, so that's going to be the natural log of 0.14 equals the natural log of our initial, which is 0.88, minus our rate constant, which is 2.8 times 10 to the minus 2 reciprocal seconds, and our time. So personally, I will take the, let's see here, we'll go natural log of 0.14. I'm going to subtract it from the natural log of 0.88. And that will get me something like minus 1.838279 equals minus 2.8 times 10 to the minus 2 reciprocal seconds. NT. We're going to divide that K to the other side and not forget the negative sign that will come along with it. And we will end up with a time of about, we'll call it 66 seconds in this particular case, just over a minute in terms of how long it will take that to occur. Any questions on that calculation there? And again, this is very similar kinetics type problems that we've seen in nuclear kinetics as well, nuclear chemistry as well. Also as well, one thing we didn't talk about that I think we talked about then, we could talk about now as well with this, just a reminder that, you know, sometimes you may not be given a number perhaps to use for concentrations. It may do something like, hey, how long will it take for it to be 50% of what it started at? And in a situation like that, sometimes very common in sort of kinetics problems that they'd use sort of percentages. And you could use the percentages in here as well. So for example, if it was a problem like that where it says how long does it take for maybe it to be 40% of what it started. And that means that you could do the final concentration as 40, the initial as 100 is one way you could do that. You could do the initial as 1 and the final as 0.4. You know, so there's a couple different ways you could kind of do that. But that's also a very common sort of kinetics question. They like to use sometimes percentages, or, you know, if they told you started though with like 50 grams and, you know, how long would it take for only 30% of that to be left, then you probably should figure out what 30% of 50 grams is and actually put the numbers in. So sometimes you'll see some percentage type problems sort of come into play when you're doing these kinetic guys. And again, you could kind of handle it that way as well by just kind of doing 100 and whatever the percentage is, or 1 and point something for the percentage. Or again, like I said, if they actually do give you a starting number, take the actual percentage of that and then plug the right numbers in. So here's our half-life equation that we've seen and talked about a number of times at this point. And by the way, if forever you can't remember a half-life equation, but you could remember sort of the integrated rate law, you could just substitute into that this part here for the final. So basically, if you took the natural log of A equals natural log of A naught minus KT, and you're good with math, you basically could substitute that into there. And if you do all that rearranging, this is basically what you should end up with by doing that. So sometimes, you know, worst case scenario, you could kind of derive the half-life equation by substituting in for the final concentration in these guys, the initial divided by 2, and then solve for T. So that's one way that you could do that. So in this case, what is the half-life of N2O5 if it decomposes at a rate constant of 5.7 times 10 to the minus 4? So in this case, we would just plug it in there, and we would take our natural log, we would take our T1 half equals natural log of 2 divided by K. And in this particular case, they gave us this. So this would be divided by, I wrote that backwards, so we'll just do that. Natural log of 2 on top, and pretend you don't see that really bad line there on the bottom. I'm gonna get rid of it. There we go, that's better. All right, so natural log of 2 over that, and that will give me an answer probably. And that answer would be natural log of 2 divided by 5.7 to the minus 4. About 1,216 seconds would be the answer there. And probably 2 sig figs based off of that. So maybe like 1,200 seconds if you want to remember that old sig fig-ness that's chemistry like. And the final part of that question is obviously, how do we know it's first order? And as we've been talking about, obviously it is the units associated with K, and the units of reciprocal seconds tells us it's first order. Any questions on that one? So again, we've sort of seen that a couple of times, or a number of times, since we did all that sort of kinetics work. So that should hopefully be familiar with you. And obviously the half-life, as we also talked about in sort of nuclear chemistry, again, is the time for how long it takes for half of whatever you started with to sort of go away. And again, here we can see in this first order, after the first half-life, we got half the circles left. Second half of that, and he continues that. About 10 half-lives or so, you probably will be out of circles or so, be pretty much gone, whatever you started with. In terms of the half-life of a first-order reaction, as we could see in terms of the half-life equation, natural log of 2 over k. So the half-life really is just determined by the rate constant, has nothing to do with sort of the initial concentration of anybody. It is just that rate constant that has an effect on it. All right, so why don't you try one here. Reaction is first order, rate constant 2.9 times 10 to the minus 4. At a given set of conditions, find what the concentration is, the final concentration after 865 seconds. So take a couple of seconds here, or minutes, and see what you come up with. Okay, so on this particular one here, again, they nice enough to tell us it's first order, but if we weren't given that information, again, we still have those units for the rate constant to tell us it is. So we want to use our first order here. And in this particular case, we are looking for our final concentration, which would be this guy. Our initial here is 0.0225 minus our rate constant, which was given to us. And our time, which was 865 seconds. So we're okay here in terms of time and our rate constant, but as I mentioned before, sometimes you're not okay with these two guys in terms of the units. So always want to make sure those guys are same units so everything cancels out correctly. And if we kind of clean up the right-hand side there, natural log of 0.0225 minus 2.9 to the minus 4 times 865 gives us the natural log of A equals something like minus 4.04508997. To get rid of that natural log, we need to take the E of both sides, basically. And when we do that on the left-hand side, that just becomes A. And if we do that on the other side there, 0.0175, and that would be molarity as it is a concentration. And we're good because it did decrease from its initial, which we would expect here in this first order reaction. Any questions on that particular one there? Okay. All right, so why don't you do the next one and see what you come up with. So we're looking for what is the half-life of this equation. Okay, so again, here we see reciprocal seconds. So even if it didn't tell us, it is first order. And obviously we want to use the appropriate equation for that, which is our natural log of 2 over K. And popping that in there, 0.271 reciprocal seconds, going to get us a 2.56 seconds. Again, when you kind of divide it there, we get our seconds that flips to the top, and we get our 2.56, which is a super quick half-life, right? That means every 2.5 seconds, half of whatever you had there is now gone, right? So that's a very, very fast half-life. You know, in like, you know, a minute, probably most of it will be gone. Any questions on first order? So again, first order, again, should be pretty familiar to you, as it is essentially, not even joking, the same thing as what we did in nuclear chemistry. So that's kind of good. But so again, obviously you need to know the graphs, you need to know the equations, and obviously how to solve for anything that's there. So much like what we did before, final concentrations, initial concentrations, rate constants using the half-life equation, time, and so forth. So all those kind of things. All right, so now let's talk then about another type of order of reaction, which is a second order reaction. And for a second order reaction, you really could get it in one of two ways. You could either get it with a single reactant that is to the second order. You could also get it by having two reactants where they're each first order, right? Which would give you second order overall. And if we get a rate law that is second order, like what we have here, and if we look at just the units of the rate constant for this guy, we would take the rate divided by the concentration squared, which means, as we've been talking about our salt earlier, one of these molarities will cancel. And what that will leave you is the typical units that we associate with a second order rate constant is 1 over molar seconds, or m to the minus 1, s to the minus 1. Just like with first order, although most of the time the units most likely will be seconds, because again, as we talked about, when we do sort of chemical reactions and stuff like that, usually we're not there for days and stuff like that. So seconds is really a most common type unit. It doesn't necessarily have to be seconds. So, you know, it could be like 1 over molar minutes, 1 over molar hours, you know, but some type of unit of time. But like I said, usually it is going to be probably seconds. because of that, we don't really do super slow and long reactions. Now, just like our first order, there are a couple of sort of integrated rate laws that go with our second order reactions, and these are them right here along with our graph. So this is our concentration and time dependence equation, and that's 1 over A equals 1 over A naught plus KT. And if we solve for the half-life for a second order, we have a half-life that is 1 over K times the initial concentration of A. So in this particular case, in a second order reaction, the half-life is based not only just on the rate constant, like it sort of is there in first order, but it's actually the initial concentration and the rate constant sort of combined. So just like first order ones and stuff, you may have to use both of these equations together to solve for something like K and then solve for it. If we rearrange this equation here and we take 1 over A equals KT plus 1 over A naught, that is our form of a straight line. That is y is equal to mx plus b. So we see that the typical linear graph that we graph for this is 1 over A, the concentration of A on the y, and on the x it is still time. And also different here is we do get a straight line, but different than first order here, we actually get a positive slope happening. And that means that when we do take the slope of it, it will directly equal the rate constant. So again, graphically, if you had the graph and like a y equals mx plus b sort of equation given to you, you could find the rate constant by taking the slope of it. And again, since it's a positive slope, our slope equals k, not negative k like it does for our first order. So much like the first order, really kind of 5 important things here, or 4 important things. The units associated with the rate constant, the 1 over A equals 1 over A naught plus KT sort of concentration time dependency equation, half-life equation, and then our typical graph that we see here on the bottom right, which is associated with a second order reaction. Now, the last type of reaction we're going to talk about, and these will pretty much encompass the majority of most reactions that you deal with. The last one is a zero order. And in a zero order reaction, a couple of the important information. If we have a rate law, the rate would equal K, A to the 0. And I believe as we talked about yesterday, if you take something to the 0 power, that equals 1, right? Which means that basically the rate here will equal the rate constant. And that means that the units associated with a zero order reaction is molarity over seconds, which is basically the same units as like the initial rate that you have here. We also have a half-life equation here where the initial concentration divided by 2K. So also here for zero order, the half-life is based on the initial concentration as well as the rate constant, kind of half of that. This is our sort of integrated rate law or concentration time one. Looks exactly like first order, except it doesn't have the negative. It doesn't have the natural log in it. So no natural logs here, but looks just like it is our zero order. And if we rearrange that equation, A equals minus KT plus the initial, that is our Y equals mx plus b. So similar things graphed. On the Y, we have the concentration. On the X, we have the time, and that will yield us a straight line as we see here, again, back to a negative slope. And the slope here will equal minus K, as you can kind of see here. Now, you may say to yourself, that looks like, in terms of the graph, the exact same graph that we did earlier with first order, and it is. When we graph first order, is the concentration of A versus time. The difference between first order, which will be this graph, and zero order, when you do that, is in first order, in a badly drawn one, we do not get a linear relationship. We get that relationship where it kind of curves, which means it's changing with time. The concentration starts to decrease. So if you do this graph and this graph, which are the same graphs in terms of what is being plotted, they will give you different types of lines. The one on the bottom, which is for zero order, will give you a linear fit. And that means we're talking about a zero order reaction. But if you get more of a decreasing with time type graph, like the one in the middle, it is a first order graph. So again, two things are being graphed there, and they're both the same thing, but the difference is the actual resulting graph will be different. If it's zero order, it will be linear. If it's not zero order, but first order, again, more of a curvature type graph will occur. Same kind of important stuff off of this slide like everybody else, previous ones. Units of the rate constant, concentration time, half-life, and graph, yes. So again, those are important things that you need to know really for all three of those guys. So first order, second order, and zero order are really the common sort of ones. And you may say, why are they the common ones? Well, if you think about a lot of reactions that we deal with, you know, they're sometimes referred to as bimolecular, which means usually they involve maybe two reactants, right? Very few reactions, if you've come across and you look at equations, right? Very few of them have 3, 4, 5 different, you know, sort of reactants and stuff like that. So because, you know, usually we kind of max out at 2 reactants in terms of, you know, a reaction taking place, that leaves you sort of these options here. You know, you could either have 1 or 2 reactants. One reactant could be zero order, right? And we have 0 overall. You could have 2 reactants where 1's 0 and 1 is 1, which give you first order. Or you could have 1 reactant that's first order as well. For second order, you could have, again, 2 reactants, each first order, and that'll get you second order. Or you could have 1 reactant that's second order. So again, if you get into 3 sort of reactants or 4 reactants, again, you don't see a lot of reactions that occur with that many reactants. So if you just think about, hey, if I had 4 reactants in my made up reaction here, and they were each sort of, you know, first order, that would be like fourth order. And again, typically speaking, not very many are happening in that fashion. So that's why typically when we talk about kinetics, 0, first, and second orders are sort of where we typically max out. Not to say it's not theoretically possible to get, say, a third order, fourth order, you know, and so forth, but in sort of everyday practice, just based on the idea of usually 1, 2 reactants is sort of the most, maybe get to 3 in some reactions as well. So again, possible maybe to get to that third order occasionally and stuff like that. But even with 3 reactants, you may have 1 that's 0 order, which will then drop you maybe back down to second order overall. So, you know, because of we don't usually have a ton of reactants happening at once, you know, 0, second, and first is usually pretty sufficient for any type of reaction that you can have. Yeah, so for example, you know, they do sort of, it does depend on certain sort of factors, but so for example, if you had, the question is sort of like, you know, how do they all sort of relate, you know, in terms of the rate and stuff like that. So if you look at just maybe, let's see here, I guess I'm going to write, here's right, maybe just write like here, I think. So for example, let's just say we had our rate equals K A to the 0, right? Which would be 0 order. We have our rate is equal to, excuse me, K A to like the first order, and you know, the rate equals K A to like the second order, for example. And let's just assume that for the sake of this argument that K is the same for all of them. And A here is, we'll just use the same value for all of them, right? We could just call A we'll call it 2 molar, for example. Right? So if we take 2 and stuff it into our first one, which is 0 order, and we'll say that the rate constant in each of them is 1. So just to keep the math really simple. So K is 1 in all of them, and say the concentration of A is 2 in all of them. So if it's a 0 order reaction, right, 2 to the 0 is 1, 1 times 1 would be 1 for the rate, right? Now for our first order, 2 to the first power is 2, 2 times 1 is 2, right? And now for our second order, if we put the 2 in there, 2 squared is 4, right? And 4 times 1 is 4 for the rate. So again, here you can see that going from 0 order to first order in this sort of condition, the rate would double, right? Going from, say, 0 order to second order, the rate would quadruple, right? While going from, say, first order reaction to a second order reaction, keeping everything else sort of constant, the rate would sort of double. So, it does have an effect in terms of the order of the reaction. And there's other factors obviously involved in terms of concentration and rate constant. But if you just kind of keep everything else constant, again, as you sort of change the overall order of the reaction, it will have an effect, for example, on how fast or slow, if you did it sort of as a first order, second order, or 0 order. Not that you necessarily can go, I want to do this same reaction as first, second, or 0. Each reaction will probably occur, the same way in terms of your orders and stuff like that. But that's sort of how they relate to each other. If you just kind of put numbers in there, you could kind of see as you go from 0 to first to second, keeping other things constant. If everybody was sort of constant amount of reactants and a constant amount of K, you can kind of see that increase in the rate as you go from one to the next. Okay. So why don't you try this one here, which is a second order reaction, initial 0.01. We're going for 5 times 10 to the second seconds. What is the rate constant? So see what you come up with here. Okay, so let's take a look at this. Here again, it tells us a second order because we're finding the rate constant. So obviously we wouldn't be able to determine the order from that. So we do want to use, again, the proper concentration time equation. And again, remember that this is second order. So unlike most of them, this actually is a positive guy there. So we have 1 over our final, which is 0.001 equals 1 over our initial 0.010 plus k, which is what we're looking for. And we do have our time here, which is, I think, 500 seconds, if I'm not mistaken. So mathematically, again, here, I would probably do like a 1 divided by 0.001. It equals, then subtract it from 1 divided by 0.01. Then divide by 500, not 1,000, 500. And we will end up with 1.8 as our value. Now, unit-wise, let's talk about units. I didn't really put it here, but this is molarity. That is molarity. So when we subtract this to the other side, it's 1 over molarity. We also are dividing by seconds. So you got something like 1 over molar seconds, or 1.8 m to the minus 1, s to the minus 1. Any questions on that particular one there? It probably wouldn't, it probably, let's see, yeah, it wouldn't actually say that in terms of it being second order with respect to R. Remember that when we talk about orders and rate laws, so rate laws and orders kind of go together, it's only the reactants are involved. So it's just the Q, which is our reactant. So that's why it's specified in terms of Q, because Q is the only reactant. So if it was second order in Q, that means that the overall order of that reaction would be second order. Again, only the reactants are involved in terms of orders and stuff like that. Other questions? Okay, so again, you need to be able to obviously solve for any of these things in terms of first, second, or zero order. And here's just a nice little table of really kind of the important info in terms of the calculation information for each of those orders. So again, zero, your concentration time equation and your half-life equation, and obviously your first order and your second order equations as well. And again, you do want to make sure you choose obviously the correct one depending on the order. And like I said, if it don't come out with sort of blinking lights like it's first, second, or whatever it may be, again, make sure that you look at the K value because you probably are given that, and that will give you the information that you need to solve for it. So this is a nice table. It has, again, those equations that are important. Basically the last two columns there. And with that as well, a very common experiment, that's the kinetics experiment that's done to graphically sort of determine, you know, what the order of the reaction is. And you could do that as well. So you could run a kinetics experiment where you basically keep track of the concentration and how it's changing over time, a long period of time. So a class that I teach, they commonly do this sort of experiment. They mix together a reaction, they put it into basically kind of like our little spectrophotometer type of thing, And they basically, the computer follows how the concentration changes over a period of time, again, based on absorbance and that color basically changing over a period of time. So for example, when they mix it together, it turns purple really quick. And then if they're not very quick, it turns colorless really quick after that. So it's able to, again, monitor sort of the change in the color over time, which would be the change in absorbance over time. And as we talked about, is related to basically the change in concentration versus time. And one of the experiments that they do is they basically don't know the order of the reaction. So essentially, once they get all that information, all the concentration over time information, you can basically make our three graphs that we talked about. You can make the first order graph, the second order graph, or the zero order graph. And again, if you graph concentration versus time, and it's the most linear, when you do like a trend line, the R squared value is closest to 1, then it would tell you that it is a zero order reaction. If you did the natural log of A versus time, and you did your trend line and you got your R squared value and it was the one that was closest to 1, it would tell you that it was first order. And if you did your 1 over A graph versus time, and it was the most linear, it would tell you a second order. So that is a very common sort of kinetics type experiment or kinetics way to determine the order of a reaction, is to simply lay up those three plots and basically do a trend line on each of those plots. And you should ideally have one that has an R squared value or a linear coefficient value, like when you do it on Excel, closest to 1, and that would tell you that that is the order of the reaction. So again, that's also a very, very common way that kinetic studies sort of do that. Any questions on first, second, zero order, what you need to know? Okay, then we're going to move on to sort of talking about the temperature relationship for a reaction and how it affects sort of the rate of a reaction, what's sort of going on as things try to proceed from reactants to products. So the first thing we're going to talk about here is we're going to look at these energy diagrams. That was a good look. Let's go back and look a little longer. So these are two typical energy diagrams that are very common for two types of reactions, as they say on top. One is an exothermic reaction, which, as you should be familiar with, right, means like a delta H value of negative, while this is endothermic, where the delta H value is positive. And again, a negative delta H value, right, implies exothermic. And overall, what that implies is that heat and energy is being released in the reaction. And that's what we see here when we actually do look at this diagram. We have potential energy on the left, and we got the reaction proceeding there on the X. And these are our reactants, and these are our products. And the major difference that we see in terms of our reactants and our products when we look at it in terms of energy is our reactants are higher in energy than our products. So in order for our reactants to get down to our products in terms of energy, basically energy needs to be given off, right? So energy needs to be given off as a result of that reaction or released to allow our reactants to come to our products. And that is your classic sort of exothermic energy diagram. Whenever you have reactants higher in energy than products, going to be exothermic. And that is opposite what we see here with our endothermic reaction. Our reactants are actually lower in energy than our products. So the same sort of just basic logic, our energy of our reactants are lower. In order for them to get up there to our products, energy has to be kind of put in, yeah, are absorbed, right? And that is your classic endothermic diagram whenever you have reactants that are lower in energy than products. Now, along the way to our products, certain things do have to happen. And basically a couple of things has to happen. They need to collide, right? So the reactants need to kind of come together and collide, which is what is sometimes referred to as collision theory. Nice little collision for them to hit. And they actually do need to hit, really two things actually has to happen. They have to hit each other really in sort of the right location. So if they hit each other in the wrong location, may not get any products to form. But if they hit each other sort of the right location, the second thing that you need to have to happen is they need to hit each other with the appropriate amount of energy, basically the minimum amount of energy required basically for that reaction to take place. And that minimum amount of energy that's required for that reaction to take place is really what is referred to as the activation energy. And that activation energy on these diagrams is really that hill that the reactants has to climb to get to the other side. So for our endothermic, it's here, right? It's this hill that it has to climb, kind of going around to the other side. And when we get to the very top here, right around here, that is pretty much your highest point in energy. And this is what is sometimes referred to as a transition state. And this little guy with the symbol here, he is sometimes referred to as the activated complex, or he's sometimes referred to as the transition state complex. TS for transition state. And basically what he is, you can see he has this little kind of weird symbol here. But basically what that means is usually what has to happen, obviously, is in order for our products to be formed, our reactants has to break apart, break all the bonds that are there. And then they have to sort of reassemble right on the other side and start to make bonds. So as it's starting to kind of proceed up the hill here and getting to that transition state, you're starting to get some of these bonds starting to break. But at the same time, you're starting to get some bonds that are starting to be made. And typically speaking, our transition state complex typically has partially broken bonds and partially made bonds happening at that point. And we could also see that it is right there at the peak of energy. And we hopefully know, right, things in chemistry, right, like to be in low energy, not high energy, right? So things that are in very high energy are typically very unstable. And this guy up here is very unstable. It doesn't usually hang around a very long time. And it very quickly will kind of drop off. That transition state guy will very quickly drop off to the other side, to the products. That's why for a lot of years and a lot of things, it's very hard to isolate that guy in the middle, because he's sort of a guy with partially made bonds, partially broken bonds, very high in energy, and again, doesn't hang around a very long time because of that. Kind of, I don't want to say unstable, but not very happy to be there. He wants to kind of get down to the other side very, very quickly. So the activation energy, which is E of A here, is basically that difference between where the reactant starts and the peak there of the hill. And down here, you can see this is where our reactants are in terms of energy, and the peak of the hill here. Again, that hill that they have to climb to get to the other side. You could also see that in just comparison of these two graphs, the one that has the bigger activation energy, or the larger activation energy, is the endothermic reaction, which does make sense. It's endothermic, so heat energy needs to be put in to kind of help everybody up and over the hill to kind of get to the other side. While on the guy on the left there, there's some excess energy. Everybody has probably a good amount of energy to kind of get to the other side. Now, how does this affect sort of the rate of a reaction? Well, you could just logically think about these things as hills. So, for example, if you had to climb the hill on the left, you probably would get to the other side quicker than if you had to climb the bigger hill on the right, as a much bigger hill to climb. So obviously, the bigger the activation energy, the slower typically the reaction will take place, because again, it's got to kind of manage that big hill, as opposed to something where there's a much smaller activation energy, things can get up and over to the other side, you know, a lot quicker. So a couple of things about the activation energy. The activation energy, as you can see in both of these hills, are typically positive numbers. Yeah, they go up. So it's typically a positive number. And usually in terms of units for activation energy, we usually see it as kilojoules, which does run into some issues in the calculation we'll talk about a little bit later on here in this chapter. But you do want to watch some of the units sometimes when you're doing some of the calculations. Any questions on that there? So what is sort of that relationship between sort of temperature and the effective rate? Arrhenius sort of came up with this sort of equation here that K, which is our rate constant, is equal to A, which is a frequency factor, and we'll talk about that in just a second. But essentially the frequency factor is sort of the proportion of molecules that do have enough energy to get up and over basically to the other side. The E of A is obviously our activation energy. R is our gas constant. It is the one with the joules in it, the 8.314. And T is our temperature in Kelvin, so everything cancels out correctly. And this is one version of sort of the Arrhenius equation. We're going to see a different version that's commonly used where they kind of come through and natural log everybody in there. And we'll see that in just a second. So again here, just a graph here for this reaction to take place. We got to break all these bonds. And as they kind of work their way up the hill here, they're breaking the bonds, starting to form all these new bonds over here. And again, up here on top is where we would find our transition state complex, our activated complex. And again, that partially made bonds, partially broken bonds, and then relatively quickly sort of drop down here. We know that this is a exothermic diagram. Reactants are higher in energy than products, so energy needs to be given off when we look at this one, and it should be exothermic overall. So as I mentioned before, when you do get to the top of that sort of energy barrier, which is the activation energy, that's where you get that transition state occurring at the very height of energy that's happening. And again, you get that very sort of unstable product, which is your activated complex or your transition state complex, which again has those partially made and partially broken bonds, and again makes it relatively unstable, I guess it's a way of putting it, because it's not very happy being really high in energy, again, as everybody sort of strives to be a little bit lower in energy. So that version of the Arrhenius equation, which relates basically the rate constant to the temperature, let's take a look at sort of the relationship that we see when it's graphed. And if we look at this relationship that we see when it's graphed here, rate constant versus temperature, we do see as the temperature increases, as we go this way, the rate constant also increases right over here. So what we see is what we sort of expect and sort of know. If we increase the temperature, typically the rate of the reaction will increase as well. And you can look at this graph and basically go the opposite way. If you decrease the temperature going in this direction, you see a decrease in the rate constant, or the rate of a particular reaction will come down. So this is sort of the relationship if you graph sort of K versus T. But a more sort of useful graph of the Arrhenius equation is what we see on the bottom. And this equation here is one version of the equation that's up on top. Basically, they came through and natural logged everybody. And when you do that sort of natural log version of that equation, it actually gives you a very nice relationship, which is typically the plot that we associate with this Arrhenius equation. This is in the form of y is equal to mx plus b. So a very typical plot, which we'll see in just a second, is on the y, you will plot the natural log of a. And on the x there, you would plot 1 over the temperature in Kelvin. And the usefulness of sort of this type of plot, which will give you a linear line, is the slope aspect of it. And you can see that from this, the slope of that line would equal minus E of A over R, which means since R is a constant, if you do this graph, from the graph, you can very quickly determine the activation energy for that reaction, because simply you just need to take E of A is equal to minus 8.314 times our slope from the graph. So you can sort of very quickly figure out the activation energy through graphical purposes. Try not to poke my eye out there. And here's a typical Arrhenius plot here. And again, the reason everything works out okay in terms of the energy is if you look at this line, the slope of this line should be negative, and the actual value of it, the number that you get if you graphed it, should be a negative number. And if you think about it, the slope is equal to minus E of A over R, which means that when you solve for E of A, it is minus R times M. And since M is also negative, negative and negative, going to turn your activation energy into a positive number. So again, that little negative there is sort of important. It will turn that activation energy into a positive number, which it typically is. It's usually a positive number in kilojoules, and obviously different for different reactions. So this is a very common sort of plot that's made. In that version of that equation that we see here on top is the version of the equation that we sort of use if you want to sort of solve activation energy, temperature, whatever it may be, sort of graphically. This is typically the equation that you use. We're going to see sort of the mathematical version of it where you don't do a graph in just a second. So just going into a little bit more about some of those things that we've been talking about here, as I mentioned, sort of the frequency factor is really that sort of fraction of guys that have the right amount of energy to get up and over that hill. When we increase the temperature, as we saw in sort of that graph, everybody gains more energy. They have more energy, and just logically speaking, if you have more energy up and over the hill, right, you're going to be able to get there quicker, even if the hill is larger, right? If you were running up the hill, right, you're going to get to the top a lot quicker than if you were just kind of moseying and enjoying your walk, right? If you like hightailed it up there, you would get up there a lot quicker. So typically, like I said, by increasing that temperature, you're supplying all the reactants with enough energy, or a greater majority of reactants with enough energy to allow them to get up and over the hill to the other side. And obviously vice versa would happen if you sort of lower the temperature. You would have a lower proportion of molecules that have enough energy to get to the other side. And that's what this graph shows. Again, T1, T2, and T2 is a higher temperature, which is the red line. And what we see is here's the activation energy. So when we reach the activation energy, we can see under the red line here, there's a greater amount of reactants or molecules that have enough energy to basically get up and over the other side, as opposed to, I guess I could use a different color, but I'll just go over a little bit just so you can see it. This, for our lower temperature, there's a much smaller proportion of molecules that would have sufficient energy basically to get to the other side. So in case you didn't like the first 7 times we saw this equation here and the information that goes with it, here it is one more time for you. And again, this is the sort of graphical form of this equation. So let's see how we could kind of use the information and a typical sort of information that's given to you in a problem that you might have to do somewhere along the way. So for example, if we were given this problem here, we want to determine the activation energy and the frequency factor for the information that's given. This is a classic sort of table that's given in an Arrhenius plot sort of problem. The nice thing about this table actually is it's given in Kelvin, the temperature. Sometimes it's given in Celsius, which means you have to convert it to Kelvin. So we do have our temperature in Kelvin, which is good. We also have our rate constant, which is good. So we would want to use our formula here to make our plot. Which again, this is y equals mx plus b, which means on the y, what we want to graph is not the k, but we would have to take all these k values and make another column and turn them into the natural log of k. And on the x, we need not the temperature in Kelvin, but we actually need 1 over the temperature in Kelvin. And we would need obviously another column to do that as well. And that would be the two things that we would graph. Again, the natural log of K on the Y, the 1 over temperature on the X. And if you did that, I would recommend something like Excel probably, unless you really like to make graphs. But you would do very much like some of the graphs that we've done over the semester here. You would do an XY scatter plot, for example, on Excel. Do a trend line best fit with your equation and your R squared value. And if you did that for this particular data, you will get this equation here, which is y is equal to minus 1.12 times 10 to the 4th. And we could use that equation to really help us solve for both the activation energy and the frequency factor. So if we look at it, we're going to just write the equation here. That was y is equal to minus 1.12 times 10, I think, to the 4x. And whoops, too far. 26.8 looks like. So remember that when we do sort of this graphical approach to this, the slope of the line equals minus E of A over R, which means if we want to solve for our activation energy, as we were talking about earlier, it would be minus R times the slope. So the slope, right, is this number right here. And important as well is, as we could see in the graph, it is a negative slope line. So putting that in would give us negative 8.314 times our slope, which would be 1.12 times 10 to the 4th. And really Kelvin. And here this would be negative as well. So we have negative, and negative is going to turn us into a positive. And we will get something like 9.31 times 10 to the 4th joules per mole. And since activation energy is usually given in kilojoules, something like 93.1 kilojoules per mole would be our answer there for activation energy, using our graph to determine that. Any questions on that there? And if you're wondering about the units here, it is the slope, so that's rise over run. So if you remember, you have the natural log of A, natural log of K, natural log of K, and 1 over T, which is in Kelvin. So it's rise over run. So natural log K won't have any units. And when you do 1 over T, the K flips to the top. And that's how the Kelvin gets up to the top, basically. Now, the other thing that we want to find was actually the frequency factor, which is the A. And if you remember that in our formula, right, the natural log of A is equal to the y-intercept. And that is, where is that? Right here. Natural log of A equals the y-intercept. So we would use that part of the formula and the information to solve for that. So natural log of A would equal the y-intercept, which is 26.8. Again, to get rid of the natural log, we're going to take the e of both sides. And that would give us an A that is 26.8, 4.36 to the 11. And typically speaking, the frequency factor will have the same units as what you see with your, where were those units? With our rate constant. So they typically will have kind of the same units as the rate constant in this case. And that's because basically it's the y-intercept. And on the y is the natural log of K. But remember, we just got rid of the natural log here by taking the e of both sides. So then it defaults back to the units associated with K, basically. So we'll end up with the same one. Any questions on how to do any of those sort of calculations there in terms of activation energy or why frequency factor using a graph? I'm imagining I'm not going to make you graph anything by hand, but if you were supplied a graph with the equation, you do need to be able to calculate these things. Any questions on any of that? Okay, so it's a good stopping place. We're nicely on pace, hopefully, to finish tomorrow. So today is the big general unknown day. So I went over most of your flow charts. For the most part, they're pretty good. Most of you missed a couple of things on it. Some of you, I did say perhaps redo the flow chart based on what I told you to do. So make sure that you redo that and you do submit that as well today before you're all done. So you'll get to watch your unknown video and identify your unknown, hopefully, and all that good stuff. So we'll start in about 10 minutes or so, and we'll talk a little bit beforehand, and then you'll be off to go and do your unknown. Yes. It's a good question. Why is it negative and it's not supposed to be? I think it's supposed to be 11. I'm just so used to writing negative, I think. Thank you. For those still here, this actually should be just positive 11. I think I had it on my calculator. I think I said it right, but I think I'm just so used to writing the negative. I wrote the negative. So it should be positive 11. All right. I'll see everybody in about 10 minutes or so. Make sure you're right here if you haven't done so already.